One other important point that we'll discuss in this lecture is the concept of boundary conditions. In one of the examples I've given in the last lecture, we had a situation where the electric field inside one conductor was different from the electric field, or actually it was the dielectric. The electric field inside one dielectric was different from the electric field inside a neighboring dielectric. And one of you asked how come this is the case, and I mentioned that we're going to understand that more when we discuss boundary conditions. So now we'll see what happens to fields at interfaces between different types of materials. So here in this case, first we'll consider the case we have two dielectrics. So there is one dielectric here, it has dielectric constant epsilon 2, and another dielectric has dielectric constant epsilon 1. The field inside epsilon 2 is called E2. This is its direction. This is its direction, and the length of this arrow is its magnitude. The field inside the other media at any point in the boundary is called E1. So this E1, and you can see both E1 and E2 can be decomposed into two components: a component normal to the boundary and a component tangential to the boundary. So this is the same thing happening here with E1. So E1 here is decomposed into E1 tangential and the E1 normal, and this all will depend on the direction of the normal to the boundary. So the normal to the boundary is also varying from one point to another. So what we'll do, we'll start by the fact that electrostatic field is conservative. So we know that electrostatic field, the integral of the electrostatic field over any closed contour must give us 0, because the potential difference between any point and itself is 0. So this is the first, this is our starting point. And we'll pick this contour L, in which we are carrying this integral, as this rectangle here. You see this rectangle here? Part of it, this part is inside the second medium. This part inside the second medium. This part inside the first medium. And when you carry out this integral has four sub-integrals. The first one is this one here. The second one is this one here, and then the two side integrals. So we have four integrals here in this case. Now, this one here will be multiplied by the tangential field inside the second conductor. So this one here will be multiplied by E2 tangential. But because of the assumed direction of E2 tangential, the product of, if I assume this direction here, this is opposite to this dl, so this product will give us a negative number. So this integral will be E2 minus E2 tangential delta L. Now what about this integral here? This integral is in the first medium, and because this line is tangential to the boundary, then we'll be multiplying here E1 tangential, the tangential component of the electric field, by delta L. Now the two sides integral may have values, but if we take the limit and make delta H as small as possible, make it actually goes to 0. So this surface will actually shrink to a very, very thin integral around the boundary. Then the two sides integral will tend to 0, because delta H will go to 0. And we are left only with the integrals over the integral over this side and the integral over this side. This one will give you E1 tangential delta L. This one will give you minus E2 tangential delta L. And this is what we have here. Sorry, it's not called delta L. It's called delta W. This is the length here is called delta W. So if you put this together and you try to make delta H goes to 0, the two side line integrals will disappear, because we are integrating over zero length, and you are left only with this integral plus this integral, and they will give you E1 tangential delta W minus E2 tangential delta W, and this must be equal to 0, because I'm integrating here over a closed contour, and the integral of the electrostatic field over a closed contour is 0. Delta W will cancel with delta W and give us the result that all electrical engineers who work electromagnetics know. That when you move from one dielectric to another, the tangential component of the electric field is continuous. In other words, if the value of this tangential component was 5 volt per meter just before the boundary, it will still be 5 volt per meter just after we cross the boundary. So the electric tangential component of the electric field is continuous across the interface between two dielectrics. So this is a very important result, and we should all remember we'll use it very often in our calculations. So tangential component of electric field is continuous. Now, what about normal components of electric fields? What happened to normal components of the electric field when we cross the boundary? In this case, we still follow the same steps, but we'll consider here instead of D, instead of E, we'll consider D. This is the direction of D2 in the second medium. This is the direction of D1. And remember, D1 and D2 are related to the electric field by epsilon, by a scale factor which is epsilon. D2 can be decomposed into two parts at any point in the boundary. D2 normal to the boundary, and D2 tangential to the boundary. The same thing is happening here. This is the D1. D1 at any point on the boundary can be decomposed into D1 tangential and D1 normal. So now what we'll do, we'll select a bell-shaped surface, okay, a Gaussian surface, and then we apply Gauss law. And this Gaussian surface is crossing the boundary. So half of it is in the second medium and half of it is in the first medium. If we apply the integral of Gauss, what does Gauss law says? The closed integral of d dot ds is equal to the charge enclosed. This bell-shaped surface has three subsurfaces: the top cylinder, the top disk, the bottom disk, and then the side surface. For the top disk, this integral will give us, because this surface is parallel to the if the bell is small size, this is parallel to the surface. So this will give me here d1 normal multiplied by delta s. Now for the other one, because I assume d2 normal to be in this direction, so I can try to draw it for you. D2 normal is actually in this direction. So D2 normal is opposite to ds. This is ds, and this is D2 normal. Then the integral over this lower disk here will give us minus D2 normal multiplied by this area. Now we still have also the side integral, the integral over the surface of the cylinder. But if we take delta H and make it go to 0, this side integral will shrink because the height of the cylinder is going to 0. And as delta H exactly reaches 0, this integral will go to 0. So the only thing that will remain is the top integral, which will give you D1 normal delta S, and the bottom integral, which will give you minus D2 normal delta S. And the charge enclosed, it is equal to the charge on the surface. If there is a surface charge density, here we assume there are no volumetric charge densities on these dielectrics. Maybe there is a surface charge density on the interface between them. So if you do that, and if this shrinks to 0, then the integral will give you the charge on this disk here, which will give you surface charge density by delta S. So as delta H goes to 0, Gauss law reduces to this expression, that this is the integral of d dot ds over the three surfaces. One of them is 0. The first one will give you d1 normal delta s. The second one will give you minus d2 normal delta s. And we know why there is this negative sign, because d2 normal is pointing into the surface and delta s is pointing out from the surface. And this will give you the charge enclosed, which is rho s delta s. So what does this tell us? If you eliminate delta s from both sides, the area of this disk, you will get that D1 normal and D2 normal are not equal. Actually, D1 normal is greater than D2 normal by the value of rho s. And remember, when we made this calculation, we assumed that D2 is pointing from medium 2 to medium 1, and the same thing is happening in D1. So here we get that D1 normal is greater than D2 normal by rho s, by the surface charge density. So this tells you that if there is a surface charge density on the interface between two dielectrics, then the normal component of the vector D is discontinuous. So if you have here 5 coulomb per meter squared, once you cross the surface, it becomes, say, 7 coulomb per meter squared, if there is a surface charge density. In reality, between two dielectrics, we usually do not have any surface charge density, unless it has been put there somehow. And so if I don't mention anything about that to you, we should always assume that between two perfect dielectrics, so no conductivity, that the surface charge density is equal to 0. And in that case, this term is 0, which is saying that the normal component of the vector d will be continuous. But what is d1 normal? d1 normal is equal to epsilon 1 e1 normal. The vector d is related to the vector e through the permittivity of the medium, and the permittivity here in the second medium is different from the permittivity here in the first medium. So we replace d1 normal by epsilon 1 e1 normal. We replace d2 normal by epsilon 2 e2 normal, which will lead us to the conclusion that e2 normal is equal to epsilon 1 over epsilon 2 e2 normal. So now we know that in general, normal component of the electric field is not continuous, it's discontinuous. And this is what we have seen one of the examples before in the lecture. So here, if the field here, this one here is, say, is 5 volt per meter, depending on the ratio of the electric constant, the electric field here may be, say, 7 volt per meter. Once you cross the boundary, there is a sudden change in the normal component of the electric field. Remember, the electric field has both normal component and tangential component. Tangential component is continuous. It does not see any change when you cross the boundary. The value just before the boundary is the value just after the boundary. Well, the normal component of the electric field will see a big change. It's always discontinuous. Okay, so this is a very important result, and all electrical engineers know that this result by heart. Tangential component of electric field is continuous. Normal component of electric field is discontinuous according to the ratio of the two dielectric constants, or the two permittivities here in this case. This will lead us to a very interesting relationship, because if we know E2, and we know the angle that E2 makes with the normal, and we call this angle theta 2. And if we know E1, we know that angle that E1 makes with the normal at the surface we call theta 1. Of course, E1, E2 normal, and D2 normal can be written in terms of E2 once I know this angle, because E2 normal will be E2 cosine theta 2, and the E2 tangential will be E2 sine theta 2. The same thing is happening here. You can decompose this electric field into two components, tangential and normal. The tangential component, actually let's start first by the normal component. Normal component will be E1 cosine theta 1 from the definition of theta 1. While the tangential component of E1 is equal to E1 cosine, this one here will be sine theta 1. So by knowing these two tangential normal components, we can obtain the expression for the angle or the ratio between theta 1 and theta 2. So let's take a look at this one here. We know that the tangential component of the electric fields are continuous. Once you cross the boundary, if it is, say for example here, it is 5 volt per meter, once you cross the boundary, it's still 5 volt per meter. So what's E1 tangential? E1 tangential is E1 sine theta 1. E2 tangential is E2 sine theta 2. What about the normal components? Normal components are not continuous. So here, once you cross the boundary, if this one here is, this may be 5 volt per meter, if you cross here, this becomes 7 volt per meter. It's discontinuous. Once you cross the boundary, it's discontinuous. So we know that D is continuous. If there is no surface charge, then D1 normal is equal to D2 normal. While D1 normal is epsilon 1 E1 normal, D2 normal is equal to epsilon 2 E2 normal. We agreed that the normal components is nothing but the magnitude of the field, or the strength of the field, multiplied by the cosine the angle. Now we have two relationships. This one here, this relationship here, and this relationship here. So if you divide this one, so if you divide one of them by the other, if you divide, say, this one by this one, you get sine over cosine will give you tan of theta 1, sine over cosine will give you tan of theta 2, epsilon 1 in the denominator. So tan theta 1 over epsilon 1 is equal to tan theta 2 over epsilon 2. Or if you multiply them, you divide by epsilon 1, so you get this expression here. This is very interesting ratio. So if we know the angle that one of the two fields components makes with the normal, we can get the other angle. We can determine the other angle by this relationship. So epsilon 1 and epsilon 2 determines for you the ratio between these two angles. which is a very interesting result from the continuity of the tangential electric field component and the continuity of the normal components of the vector D. Now let's consider a couple of examples on this concept of continuity of tangential of electric field and the continuity of normal components of the vector D. We have, consider the figure shown here. We have the field in two different media. In the second medium here we have E2. It makes an angle of 30 degrees with the normal to the surface, and we know that the magnitude, the vector E2 has a magnitude of 10 volts per meter. We'd like to calculate the magnitude and the angle of the vector E if the ratio between epsilon 1 and epsilon 2 is 1/2. So here in this medium here, epsilon 1 is 1/2 epsilon 2 here. So we have an interface between them. We'd like to calculate the strength of the vector E1 and its angle theta 1 with the normal. Of course, this is a direct application of the theory we considered. What we'll have to do, we have to get the tangential component of the vector E2, and this will be still the tangential component of the vector E1, because tangential component does not change once you cross the interface between two dielectrics. We have to get the normal component of the vector E2, and then we apply the appropriate ratio to get the normal component of E1. Once we have done that, we know now the normal component of E1 and the tangential component of E1, and we can solve for E1 and its angle. So we apply the two rules that we know. We know that the tangential component of the electric field is continuous. It does not change. Then E1 tangential must be equal to E2 tangential. What's E2 tangential? From the definition of the tangential field, it is the strength of the electric field sine theta 2, because theta 2 is the angle with the normal. So we know what is modulus E2. We know what the strength of the electric field in the second medium at the interface. It's 10 volt per meter. We know that theta 2 is 30 degrees. Then its sine is equal to 1/2. So we know that the first field, just when you cross the boundary, the tangential electric field in the first medium will be 5 volt per meter. Now we know that normal components of the electric field is not continuous, but they are related through a ratio of epsilon 1 to epsilon 2. So we know that epsilon 1 E1 normal is equal to epsilon 2 E2 normal. This is D1 normal and this is D2 normal. So the vector D is continuous, but the vector E is not continuous. So now we can say that E1 normal is equal to this ratio, epsilon 2 to epsilon 1 E2 normal, and this one here is equal to 2, because epsilon 2 to epsilon 1 is equal, the ratio is equal to 2. Epsilon 1 is 1/2 epsilon 2. Can we get E2 normal? Of course we can get E2 normal, because we know the modulus of E2, it's 10, and the angle is 30. So it's 10 cosine 30 degrees. So by that we can get the normal component of the electric field in the first medium. So we continue our calculation. We get that E1 normal is equal to, this is the ratio, this is epsilon 2 to epsilon 1, we agreed, it's equal to 2, this is given. This is the strength of the electric field E2, and this cosine 30 degrees. When you simplify that you get that E1 normal is equal to 17.32 volt per meter. So now what we have the vector E1, this E1 here, we have its normal component. This is E1 normal, and we have its tangential component. We have E1 tangential. We want to get this angle theta here. Of course, we can get this angle theta because the E1 normal is equal to E1 cosine theta 1, and the E1 tangential is equal to E1 sine theta 1. Then we can simply say that tangent of theta 1 is equal to E1 tangential over E1 normal. We calculated this one to be 5 volt per meter. We calculated one to be 17.32 volt per meter. When you divide them, you get 0.288. You get 0.288. And when you get the inverse tangent of this one, you can get 16.06 degrees. So we know that the vector electric field in the first medium makes an angle of 16 degrees with the normal. If you want to get the modulus of the electric field in the first medium, is not a problem, because you can see the strength here is equal to square root of E1 normal squared plus E1 tangential squared. And this is the expression I use here. The one of them is 5 The other one is 17.32 as shown here in this expression. So when you do the square root and you sum them, you get 18.027 volt per meter. So now we know what is the magnitude of the electric field in the first medium. We know its angle with the normal to the interface. We consider here one more example. We have this in cylindrical coordinates. We have a cylinder for rho less than or equal to 2. So for inside the cylinder of radius 2, the dielectric constant is equal to 2. And this is the expression for the electric field. For rho greater than 2 meters, epsilon r is equal to 3. So we'd like to get the electric field for the region epsilon r greater where epsilon r is equal to 3, or when rho is greater than 2. How we can get this field? This is what we have to consider. Of course, here the surface, the interface is at rho equal to 2. And it's very important in all these calculations to determine what is the normal to the interface. And once you have determined that, then the tangential component remains continuous. The normal component is discontinuous. So if we try to draw a diagram for that, we have a cylinder. Inside the cylinder, there is a certain epsilon. Outside the cylinder, there is a completely different epsilon. This is the electric field inside the cylinder. This is the electric field outside the cylinder. And because of the definition of the boundary, the normal here to the boundary, if you can see, the normal here is a rho. Then the tangential component is all components of the field normal to a rho. So the tangential component will give you the two components E phi and Ez. So E phi and Ez will not change when we cross from inside the cylinder to the outside of the cylinder. What's going to be changing is a rho, because of the change of epsilon. This is what we call the normal component. So it's very important for you to determine what do you mean by a tangential component, what do you mean by a normal component. It's all related to the normal to the surface. The surface here is a cylinder, then the normal to the surface is a rho, then the tangential component to the surface are a phi and Az, while the normal component to the surface is the e rho component. So starting with the electric field given, we have this is the electric field given to us. It has a rho, phi, and z components. Then we know that this is the tangential component to that cylindrical surface. It's the phi and z components. And this tangential component will be transmitted as it is. It does not change. Then we know that outside the cylinder, the tangential field E2 will have tangential component E2 tangential, 6a phi and 9az, which is the same one as the first one. Now, the normal component here in the first medium is 3, and we know that the two normal components are related through this expression. Then we substitute for epsilon r. Epsilon r1 is equal to 2, epsilon r2 is equal to 3. Then we know if you multiply this one by 3, you get that this in the second medium, the normal component which will be in the rho direction is equal to 2. So now we can tell that the second field, E2, has component of 2 in the normal direction, so 2 in the rho direction, and the phi and the z components are aren't changed. So this is a new expression for the electric field inside the second dielectric here with epsilon equal to epsilon 2.